Hi, it's Matt, and in this video we're going to talk about the fourth postulate of quantum mechanics. So what does the fourth postulate say? It says that the average value of a measured physical observable, which we call the expectation value, can be computed by this formula here. So let's talk a little bit about it. First, in green, on the left-hand side, is the expectation value and of the physical observable corresponding to the operator omega. So again, omega hat here is our operator. So when we put these brackets on the side, that means the expectation value of that operator. Next, let's move to the right-hand side. We have psi q of t is our normalized wave function. And of course, this here is our complex conjugate of that. This is the wave function we describe in the first postulate of quantum mechanics. And then in pink, that's just the operator corresponding to the particular physical observable we're finding the expectation value of. So let's talk a little bit more. So what exactly is the expectation value? So first, let's review from the third postulate of quantum mechanics and just remind ourselves that every time we measure a quantum system, so we get the values of those physical observables, we're always going to get an eigenvalue when we take that measurement. But now let's say we measure that eigenvalue, got the value of the physical observable, an infinite number of times, and then averaged all of those values. So the infinite number of measurements, that average of the infinite number of measurements would be our expectation value. So now let's talk about two things our expectation value isn't. First off, the expectation value does not need to be an eigenvalue. Because again, we get our eigenvalues an infinite number of times and then average all of those. That average doesn't have to be an eigenvalue. And again, based on that, our expectation value does not need to be an eigenvalue. Similarly, the expectation value is not the most likely value for a measurement. The only thing the expectation value is what's shown by the second bullet. The average value of an infinite number of measurements of our physical observable. So now, let's do an example. Let's find the expectation value of our position, so x hat, given this wave function here. And I will tell you that this wave function is already normalized. So we're going to first write our general formula, that our expectation value is the integral across all space of the complex conjugate of the wave function times the operator applied to the wave function. So first, let's plug in. So we know that all space in this case, since we're in one dimension, is going to be negative infinity to infinity. And then we're going to rewrite psi conjugate qt as just psi conjugate of x, because we know our wave function is just a function of x. Similarly here for the right side of our equation. And then finally, in the middle, we're replacing a generic operator with our position operator, because that's what we're finding the expectation value of. So now, let's actually plug in our operator and our function. So we get our expectation value is our integral across the complex conjugate of our wave function. We'll notice it's just the wave function, because our wave function is real valued. Our x hat operator, our position operator, just tells us to multiply by x, and then we have our function. So now let's simplify this a little. We know that the fourth root of 2 over pi times the fourth root of 2 over pi is just the square root of 2 over pi, and we could take that out of our integral. So we get that the expectation value of x is going to be the square root of 2 over pi times the integral from negative infinity to infinity. We have our x from our operator, and then that's times e to the negative x squared. But when we take that integral, we're just going to get 0. And to figure that out, you would plug that into an integral calculator. So we get that the expectation value is the square root of 2 over pi times 0, or our expectation value is 0. What this means physically is that the average value or the expectation value of the position is 0, right in the center of our x-axis. So let's do a second example. We're asked to find the expectation value for our angular momentum in the z direction, or LZ hat, given the function 1 over square root 2 pi e to the negative 5I theta. And we're given here that we're going to be integrating from 0 to 2 pi, because we're given that's what all space is for theta. And finally, in the box is just the definition of the LZ hat operator. So the first thing we're going to do is write our formula, given to us by the fourth postulate. Expectation value is equal to the integral across all space of the conjugate of the wave function, operator, wave function, d tau. Let's plug in a little. So we know we're looking for the expectation value of LZ hat, so that's what we write on the left-hand side. And let's plug in 0 to 2 pi for all space. And you'll see we just cleaned up a little inside the integral by getting rid of the qt and replacing it with theta, our integral, our variable of integration, and plugging in LZ hat for the operator. So now let's plug in our function. So we have the expectation value is integral 0 to 2 pi, and then it's going to be the conjugate of 1 over square root 2 pi e to the negative 5I theta times our definition of our operator, negative IH bar d theta, then our wave function d theta. So first, let's take the conjugate of 1 over square root 2 pi e to the negative 5I theta. Remember, the conjugate tells us to replace everywhere we have an I with negative I, so our exponent becomes positive. So we get our expectation value is the integral from 0 to 2 pi of 1 over square root 2 pi e to the 5I theta times negative IH bar d theta applied to 1 over square root 2 pi e to the negative 5I theta. From here, let's get all of our constants out of the integral. So constant-wise, we have 1 over square root 2 pi, negative IH bar, and then 1 over square root 2 pi. Taking all of that out of the derivatives and the integrals, we get that our expectation value is negative IH bar over 2 pi times the integral from 0 to 2 pi e to the 5I theta times the theta derivative of e to the negative 5I theta d theta. And now we take the derivative. So using our derivative rules for exponential functions, we know that the derivative of e to the 5I theta is just negative 5I times e to the negative 5I theta. So now we're just going to move to a new slide, so the top of this will disappear, but the question will remain. So this is the same thing we had on the previous slide, nothing's changed yet, but now what we could do is we have another constant to take out of the integral. We have another negative 5I we could take out. So let's take that out. And doing so gives us our expectation value is negative IH bar times negative 5I all divided by 2 pi times the integral from 0 to 2 pi e to the 5I theta times e to the negative 5I theta. However, it should be noted that these exponents sum up to 0, so that's the same as e to the 0 or just 1. So simplifying, we get our expectation value is negative 5h bar over 2 pi. Again, that's just simplifying the constants on the outside, times the integral from 0 to 2 pi of 1 d theta. But that integral, we know, is just going to be 2 pi. So we get our expectation value is negative 5h bar over 2 pi times 2 pi, or that our expectation value is just negative 5h bar. And that is our final answer. That's all I have. Thank you so much for watching and have a great day. Leave any questions you have below. Thank you.